Hello students, welcome back. Previously, we went through the definitions and some elementary examples of rings and fields. Now the next step we have to take is the uniqueness lemma, which is, as a matter of fact, very, very important in terms of theory, but technically it's trivially simple. That's why it used to be de-emphasized in gray. Here we go. Let R be a ring, then it has one and only one additive identity, because if it has two, then they're the same. So we can call it the identity. Does it ring a bell? As a matter of fact, we did it already. We did it for groups. We used to use e's instead of zeros, and the star notation for group operations rather than plus notation. It's the same as before. Now the same thing goes for the additive inverse. We did it already in groups. For each element, it has one and only one additive inverse, because if it has two, then they end up with the same. The proof, again, exactly the same as before. You can do the same thing for multiplication version. If you have two unities, then they're the same, and the multiplicative inverses as well. So important in terms of theory, because these allow us to use all those identity and inverses and unities and so on freely, because they're all unique whenever they exist. But technically, just a triviality, something we already went through in group theory. Okay, all right, what's next here? Some properties of identities and inverse. Okay, all right, what's the first property? This one de-emphasized in gray. What is it? Double negative. So the inverse of inverse is original. Okay, all right, how do you prove it? Actually, trivially simple. What do you mean by the inverse? If you add up, you'll end up with 0. That's what it means by the additive inverse, right? So negative a is the inverse of a, so add up, then you're going to get 0. But then again, this a is the inverse of negative a by the same token. And of course, we already proved that the inverses are unique for a given number. So if you get 1, that is the inverse. Anyway, that's a proof, but yeah, too trivial. So let's just go back to where they were. Too simple. Important, yes, but too simple. How about the next one? Oh boy, this one is important, and it's not that trivial either, so let's work on it. So how do you prove it? Well, we have actually two equalities. This is equal to 0, or also this is equal to 0. Let's see, let's prove this one. And the other one is left to the students. So how do you prove that? Well, my suggestion is use this observation. 0 is 0 plus 0, because 0 is the additive identity. Does it make sense? And then we can use a distributivity. A times 0, too much space there, plus a times 0, like this. Now, if you skip this middle line, then you see that a times 0 is a times 0 plus a times 0. So you can subtract the same thing, a times 0, from both left-hand side and right-hand side. Let's go ahead and do that. A times 0 minus a times 0. And right-hand side, a times 0 plus a times 0 minus a times 0. What do you mean by subtraction? That is just adding the additive inverse and the additive inverse is unique. So it is well-defined operation. And then, of course, adding an additive inverse, what do you get? The left-hand side is, of course, 0. Therefore, left-hand side is 0. And the right-hand side, what do you get? A times 0 plus, what is this? Subtracting itself, that's 0. And adding 0 will not change anything, so that's what you're going to get. So a times 0 is 0, as we wanted. We proved this part. How about the other? 0 times a is equal to 0. That part is left to the students. You can do pretty much the same way, except that parenthesis is coming to the left, and you'll have to distribute from the right. And is that what I did here? It's a proof. Oh, I did the other one actually. Yeah, broke off and then got, yes, same thing. And this one is left to the student, but wait a minute, that's what we already did. So we ended up doing both of them. I should have selected the first one and left the second one as your homework. Okay, all right, let's go to number 2. Okay, this time, apparently I'm using the first and the third, so let's do this. Prove that's equals to negative of a times b. Let's prove that. And then the other one is left to the student. Let's prove that. So how to prove this is negative of that? Negative of that, that means this thing is the additive inverse of a times b. Make sense? That's what this negative is talking about. The additive inverse of. So additive inverse, well, what's the additive inverse? What do? They add up to 0. So that's what we're going to do. A times negative b plus a times b. And let's see if this turns out to be 0. Okay, do you see that a is common? So I can factor out. Okay, a is common, so I can factor it out. And then I get a times 0 because negative b plus b is 0. And a times 0 is 0, which I proved earlier. So if I skip this middle part, what do I get? A times minus b plus ab is 0. I don't need this parenthesis, by the way. So flip this to the other side. A times negative b plus a times b minus a times b is 0 minus a times b. And this is 0, right? So that just goes away. And 0 minus of that, okay, all right. Yep, flip this to the other side. That's the proof. So that's what we wanted. And that's the proof. Let's see, is that what we did here? Yep. Distribute a, factor a out here, and then flip this to the other side, yes. And then I left this one as an exercise for you. Yeah, okay, all right. This one I didn't do. Same thing, similar idea. This time b is common. The detail is left to the students. Okay, we proved these 3. Now how about this one here? So that's what you have to prove. How to prove that? Let's see, from this left-hand side, let's use something we already proved, and let's go to this number 2. You see, please recognize that this negative b, I can pull it out to this number, the first number, so I get negative a. See that? This negative b which was in the left-hand side, which was in the second term, second factor, it moved to the first factor. Let's do that. Let's move this. So we get negative of negative a times b. Make sense? This red moved here to the first number. Just like here. This negative b will become positive b, and this had negative. But here we already started from negative a, so we have double negative, which is just a. Zero and 2. We use these two. And let's go back to black. Yeah, technical proof may be trivial, but yeah, okay, alright. So it's a one-liner. What did I do here? Oh my goodness, as a proof. Oh wow. It should work, it must be right. Oh wow, it must be right, but I think this one better. Yeah, I think this is better proof. Simpler, certainly. Using this one here. Moving this negative from the second factor to the first factor. And first factor started with negative, so we have double negative. So they disappear. Yeah, this proof is, in my opinion, simpler and superior. This one works, but I don't know what I was thinking. Looks like I was not clever enough when I wrote this notebook. Okay, anyway, we got all those. So double negative, original, something times 0 is 0. And then negative times positive, or positive negative times negative is negative. Negative times negative is positive. Yeah, we proved those kind of things. They all apply for all rings. Let's see, we still have a couple of topics here, but they are really short topics. Just some names. Let R be a ring with unity. An element U is called a unit if it has multiplicative inverse. Remember, not everything has multiplicative inverse. If every non-zero element has multiplicative inverse, then that ring is called a field. That commutative ring has to be field, excuse me. This ring doesn't have to be commutative, so okay. An element with multiplicative inverse is called a unit, and every non-zero element is a unit, then it's called a division ring. Division is possible, but not necessarily commutative. The multiplication may not have to be commutative. Now, commutative division ring is called field. So multiplication is commutative, and then also divisibles. Non-commutative division ring is called a skew field. Okay, example of skew field, think about that. I have one here, quaternion group, but too complicated. And then, if you select all the units, then it forms a multiplicative group. You can prove it. And then we denote it as Rx. And if the set of all non-zero elements of a field, then in this case of Fx, we use the same notation. And good example of that is a general linear group. The set of all non-singular square matrices of size n. And yeah, this is a skew field because we have multiplicative inverse on everything, yes, but the multiplication is not commutative. And then quaternion was another example, but that's a bit too hard. And that's where I'm going to stop. I don't want to go too deeply into those skew field and division ring and things like those.